Since last year, one of the major things that we have changed is to really switch a little bit from the original proposal to rely exclusively on using glass to make the infrastructure. But instead, we have looked into just the landfills. What kind of materials are going to landfills? And it turns out that there's a huge abundance of PET, plastic, high-density polyethylene, and also aluminum cans, in addition to some glass bottles. So we started to design a system of MEERs that for agricultural applications based on exclusively things that we throw away.
Welcome everybody to another Climate Emergency Forum session, and this one is being filmed by our team in Sharm El-Sheikh, Egypt at COP27. And like most days here, it's about 29 degrees and 40% humidity, so it's pretty hot. But I did manage to put on the monkey suit anyway. And I have with me here Dr. Yi Tao. We're going to talk all about the MEER concept to cool the planet. Dr. Tao has been working on this and actually presented at the last COP in Glasgow, and we had a chat about it. So this is an update on what he's been up to in the last year, the improvements he's made to MEER. So,
glad to be here, and I think yes, since last year, one of the major things that we have changed is to really switch a little bit from the original proposal to rely exclusively on using glass to make the infrastructure. Because as time went on, it becomes clear that it's just not possible to really demand society to ramp up the production of a particular kind of material in order to do climate cooling. But instead, we have looked into just the landfills. What kind of materials are going to landfills? And it turns out that there's a huge abundance of PET, plastic, high-density polyethylene, and also aluminum cans, in addition to some glass bottles. So we started to design a system of MEERs that for agricultural applications based on exclusively things that we throw away. So this way, we not only would be able, to address the global warming issue and the local sustainability issue, but also we would be diverting the waste stream and solve potentially a large part of the landfill problem that's also plaguing many parts of the world, including countries like the United States, where like more than 50% of such materials are still going to landfill. So that's one of the major changes. And with that comes another co-benefit. The weight of the system drastically reduces, because instead of like 4 millimeter glass, which previously weighed several pounds, a sheeting of the same area is essentially weightless. So the emission associated with shipping these things, from production centers to the end user, now turns out to be completely negligible, and that would also help, popularize this method and make it more sustainable and overall actually carbon negative. So that's one major advance that we have made since COP26.
Thank you. And I think you've also found a lot of ways to have co-benefits with these MEER arrays. So one example that you give, which is very interesting, is an attempt to cut down on water loss from reservoirs that are feeding hydroelectric plants, or also just reservoirs for drinking water, by putting these mirrors. I think you tried experiments where you put the mirrors underneath the water a little bit, had them floating on the surface of the water and had them elevated slightly above, and you found that you could greatly cut down evaporation rather from the reservoirs. And also there's some other co-benefits of having them over farmland. You can keep the soils cooler. And you also did experiments where, or got data where you found that you could actually block something like 30% of the light going to various crops and not having the yield suffer. So can you maybe discuss a few more of those proposed things? And the other thing was to cut down on the urban heat island in cities by having them on on roofs. So this is all, these things would all benefit the climate, above and beyond the reflection of shortwave radiation causing the actual cooling. So maybe you could elaborate on some of those.
Yeah, thanks for the question. I think all of these recent conceptual advances and also the ensuing experiments are also the result of the same line of thinking, that it's not really feasible to ask that society, governments to start a whole line of just a global cooling MEER business, but rather we have to just see what needs there are in order to incorporate the technology in ways that help existing needs. So one of the major challenges facing the global food system is access to fresh water. And currently over the globe in irrigated regions, every year we're having a water deficit that's about 120 cubic kilometers. So that's a combination of overdraw from groundwater and also surface water, so leaving less for ecosystems. That's a very bad problem. But the silver lining in this is that if one does an inventory of how much fresh water is being lost from artificial reservoirs, the number is rather stunning. The total loss on an annual basis is 300 cubic kilometers, which is almost 3 times the amount of deficit that's coming away from irrigated agricultural regions. So the implication of the huge amount of water, 300 cubic kilometers that's lost by evaporation, and the need for 120 cubic kilometers to fulfill the deficit means that if we dropped the evaporation from these reservoirs by a third to a half, we would be able to, at least temporarily, resolve the freshwater shortage issue. So we did these experiments, floating MEERs in this example at 85% coverage above water, on the surface of water, and also below the air-water interface. What we found was that we could drop evaporation by up to 70% by, say, 80-90% coverage. And more strikingly, the temperature of the water could be cooled by up to 10 degrees Celsius, especially during the heat of the day. So if you imagine, if we apply these sheetings, over coral reefs and other vulnerable coastal ecosystems that are devastated by marine heat waves, we could have the hope to temporarily provide alleviation away from these just deadly events. So that would have a ecological application as well. So MEER sheeting in water systems can provide freshwater saving, but also ecosystem protection. And here in Sharm El-Sheikh, when we were flying in, it's a like desert landscape dotted with private compounds, each of which is equipped with its own swimming pool, mostly empty, just sitting out there evaporating water. So it's for somebody who works on water conservation and finding ways to combat that, it's really disheartening to see all of that happening. I think Paul also asked about application in agriculture. So this system based on hybrid PET devices, glass, and bamboo is indeed custom made to be deployed in agriculture settings and also be able to capture a fraction of the rainwater that falls down, because in global warming there's climate extremes, extreme rainfall or drought, so they come erratically, so when it comes down generally it's too much. So our system would be able to capture and store part of that proportional to the aerial MEER coverage for use later in hopefully drip irrigation. So that extends the run for humanity, at least as we find times to decarbonize and also scale down the economy in a way that's sustainable and compatible with general health and well-being.
Yes, no, this is great. And there was one with urban heat islands. Have you done, if houses had these mirrors on the roofs, you could significantly offset the, and large cities are, it's quite a significant effect. The city can be, 2, 3, 4 degrees warmer than the surrounding countryside. And the urban heat island effect also changes the weather because there's less rainfall downstream from the cities because of this heat dome over the city. So you've also got some mounted on a roof in your presentation. Now, is this your house is that your house with the mirrors on the roof? I was just curious.
Well, I wish I had a house, but I don't know what to do with it. Anyways, I'm a nomad and I'm homeless, so I couch surf with friends who are gracious enough to not charge me rent as long as I cooked for them. So it shows that people can live with much less resource than we think we need. But no, the roof was donated by one of our MEER members, Bill Dillon, who is a licensed contractor. So he's gracious enough to basically help us with the logistic aspects of this, including donating the roof. So it's a 2-story building with 3 apartments on each floor. And we chose the central apartment for the experiment because it's less exposed to the sidewalls on the other sides. And what we found was that you have cooling for different parts of the building depending on where you measure. If we measured on top of the roof itself, we could measure up to 30 degrees Celsius of cooling during the heat of the day, which is 60 degrees Fahrenheit roughly, which is quite significant. We can also measure directly underneath the roof in a cavity, in this case, an insulating cavity. In that space, the air temperature dropped by 15 degrees Celsius or 30 degrees Fahrenheit, and that space is very comparable to where low-income communities live in the global south, where they oftentimes don't have more than just a sheet of metal or some layer of cloth above their heads. So if we apply this technology, passive technology, to places like India or Pakistan suffering from these extreme heat, we could dramatically reduce their exposure to deadly heat events by the order of several degrees to tens of degrees Celsius. And in the global north, we're still investigating the impact on electricity usage, but even in insulated spaces, we can measure about 1 or 2 degrees Celsius, like 3 or 4 Fahrenheit of reduction, which is non-negligible. So that's one aspect for the immediately local impact. But we have to remember that we're only covering 1 roof out of 3 in even just 1 small apartment building. And the impact is expected to grow, and the sum is more than just the sum. Because when you only have the central one covered, heat from the neighboring apartment will then leak into the central apartment, which is cooler, so thus degrading the overall impact. So if you had, say, all 3 apartments covered, then the impact might be even more than what we measured. And that's something we seek to understand in the next measurement cycle, unfortunately next year, because the summer comes and goes. And then what's beyond the single building level is neighborhood level. And then at that level, we would expect to measure air temperature differences, not only structural differences in temperature for the building itself, but then the lack of heat generation on the roof means less heat transferred into the air, so the air will be heated less, and that cool breeze of air would go to the next building, then also contribute to cooling down your neighbors. So it's something that's synergistic. So if you had everybody working on this, then neighborhoods could be cooled by tens of degrees Celsius in air temperature during the worst of heat waves. So that would be very useful for city planners who are trying to combat this urban heat island effect. Of course, eventually we have to understand how the single block scale to city scale, regional scale, and global scale impact would scale. So in order to understand that, we need to measure at multi-hectare to kilometer square scale the impact to atmospheric circulation. So when you have perturbation to how hot air rises and how they circulate in the troposphere, then understanding that process is the first step. So we're actually have established collaboration with the Romanian National Laboratory for 3D Atmospheric Studies. They're happy to devote their whole institute's measurement instrumentation to study MEER at a 1 hectare scale, so 100 meter by 100 meter scale. We're invited to cover their research campus with MEERs, but right now we don't have the funding to do so. So for all of those of you watching, if you could help us, start this very crucial experiments that bridges the single family scale, neighborhood scale, to eventual regional scale application, and hopefully demonstrating global impact, would be very helpful if you could help MEER through donations and any way that you can.
Yes, thank you. Very, very fascinating. I think the MEER technology has huge potential. It makes me quite excited. I said to Charles last night, I said, I just read your presentation in detail and said to him, that's it, climate change is solved now. We don't have to worry, we can all relax and go home from the conference, right? So, and the other thing, Yes. No, of course. That's in jest a bit, but also I always think of I have a bit of a devious part of my character, and I'm thinking, if you don't like your neighbors, you can tilt all the mirrors and aim the light at their house, right? Or now this is not a new idea, because I think the Greeks back hundreds and hundreds of years ago, they used mirrors from the shore to try to shine light on ships to set them on fire, with some success, I think. And there's also a town, I believe, in a valley in the Alps where that gets no sunlight. So they put mirrors at the very top of the mountain pass, and they control the angle, and they direct sunlight so they get some daylight, some sunlight into the village. So there's lots of different applications. So changing topics a little bit, the global dimming effect, where you have the aerosols. Okay, I always thought that the most likely number for global dimming factor, the global warming that's hidden by the aerosols blocking sunlight, and also in the direct effect, and also acting as cloud condensation nuclei, forming low-level clouds in the indirect effect, both of which will block sunlight and cause some cooling to offset the warming. I thought the best number was about 0.5 degrees Celsius effect, but it turns out that a recent paper just from the last month using ship trails shows that number is closer to 1 degree Celsius, or 0.9, and with a climate sensitivity of 0.9 degrees Celsius per watt per square meter. If you multiply that by the radiative forcing of the aerosols, minus 1.2, you get a factor of about 1. And so this is double. And in the computer models, they're using the old numbers, of course. It makes MEER more important. As we clean up emissions and reduce aerosol production from industry, the warming is going to be worse than we thought. So MEER is vital. Now, can you talk a little bit about the geographical placement of mirrors? Like, would we want to put mostly the mirrors in places where there's aerosol sources now on the planet?
Yeah, that's a very important question, the placement of the mirrors. Obviously, the amount of this hidden warming is different depending on where you are, depending on the current fuel mix and the quality of the coal. So right now, most of the aerosols are found in East Asia and Southeast Asia. So if we were to decarbonize just blindly, we would be exposing those regions to the largest shock in suddenly increasing the local amount of sunlight reaching the ground. So recent examples, in 2020 and in 2022, India and China suffered some of the worst either extreme flooding and extreme drought, and both of which can and have been attributed to this sudden tiny perturbation to the aerosol loading. So we know it's a powerful effect. And even in the United States, a paper that came out this year tried to seek for association between forest fires and also the changing aerosol due to lockdown in the United States. They also found roughly 1/3 of the abnormal temperature, abnormal humidity, abnormal rainfall could be quite robustly attributed to this aerosol level decreasing. So in both the Chinese study on extreme flooding and the American study on the wildfires, roughly 1/3 of the observed anomaly, so the observation, 1/3 of the observation could be attributed by computer models to a change in aerosol. So that leaves the question, where does the remaining 2/3 come from? So I'm only citing like 2 examples, but there's other studies also suggesting similar ratios of attribution. So the computer models are capable of capturing just a portion of the observed problem. So exactly that, the remaining could be just because we haven't entered the full aerosol cloud interaction into the models. So as the paper that came out in Nature on October 5th demonstrate, invisible ship tracks also contribute to global dimming. And because they were formerly invisible, we didn't care to count them. So perhaps the remaining 2/3 of the anomaly that current models are not able to explain, even though the patterns perfectly match, could be due to this invisible component that has not been fully recognized. So then the implication is that, yeah, we have in store for us a lot more hidden warming than even I myself suspected just a year ago. So that makes replacing, the dimming effect of pollution using strategically placed, say, ground-based infrastructure like MEER all the more important. And now to the question of where to put them. Obviously, if we want to maintain current climates, assuming a stable, slow, controlled descent of fossil fuel burning by the end of the century, we need to cover roughly 20% of global cropland. That's 2% of the Earth's total surface area. But luckily for us, there's a lot of cropland to work with, and many crop types are able to tolerate substantial shading, and actually many prefer to be shaded, like tomato and the fruits and olives and also grapes. So for the wine lovers out there, so it's something you need to do anyways, even if you didn't know about it. And people use different nets, like usually dark, black, red, sometimes white, to do the shading to decrease how much light is. So people in agriculture, anyways, has been using colored nets for quite a few years with great success in improving both the quality of the appearance of the fruits. You don't get stain on your one side of your apple, and also they are overall give you more biomass per hectare. So it's something that's just straightforward to switch to a mirrored system, where you not only have the local cooling, you also cool the air more than colored nets. You also cool the globe, so it's a multiple benefits at the same time. And the amount of material used using our latest generation of mirror devices is actually less than the nets. So we also save our material and the plastic waste problem. So that's where the project stands, I guess.
Okay, so when you put the mirrors in agricultural fields, how do you ensure that the crops can still be properly harvested without losing yield?
Excellent question, because most farmers they like to stick to existing protocols, and it's would be a huge uphill battle to not only convince the farmers to change their ways, but also change the whole industry of how farming machineries are made. So we are thinking about this problem in several parts. First of all, in the case of like orchards or vineyards where there's a lot of manual labor, I don't think that's an issue, because you can just get in there, and the heights of these are like 2 meter, 2.50 m, so people can get in there comfortably, and it provides shading during the harvesting. So why not? So it's not really perturbing them. In the case of crops that are sensitive to light, which includes some of the grains, especially corn, maybe we just leave the corn alone and just let them do as they always have. Because frankly speaking, we have enough surface area with the other crop types and also forage crops, basically grassland, in order to have enough area for the mirror implementation. And in the case of just growing hay, we could devise systems where we can quickly dismantle the mirrors and move them out of the way, because they're essentially plastic sheets, then to just clear the path for the machine to pass through before we either put them over or leave them out during the winter, depending on your local needs. So exactly that brings down into the question of the timing during the season of when you should put these things out, because and that's something we need to answer with more experimentation, obviously during the summer when there's heat waves, and that's also the largest global cooling benefit would come from when there's abundant sunlight. But whether we keep them out in winter to do some partial cooling, or maybe the impact might reverse, who knows, because then they could also prevent heat from escaping from ground. That's something we need to investigate. So that's another question, just the frequency of putting them on, taking them off. But since they are plastic sheets, that's lightweight, it's not too much trouble to just spend 2 minutes to roll them up. For example, you can devise rolling systems.
Okay, thank you very much, and I'll thank you now for this wonderful highly great potential work that you're doing. Just a couple in concluding, maybe you've mentioned scaling up with different projects on university rooftops. I think the nice thing about this technique is it's very scalable. For example, when you're building new buildings or replacing roofs in a city, I could see this material could almost become like a roofing material, especially if it's durable. Asphalt shingles, which are used commonly on roofs in North America, they last about 20-25 years. So if the mirror technology is durable, it could replace many roofs, public government buildings, like bus stop roofs even. you know, you could even have structures, you know, there's not enough shading, I think, in places, you know, like where we are here in Sharm El-Sheikh. I mean, as you're walking along the streets, it's hard to find shading. And so even little systems along on top of sidewalks, for example, in cities could be very valuable. So there's lots of, I'm trying to think, I'm sure you will come up with, and you know, maybe others will come up with other co-benefits of this technology. But so I guess you'll be looking at that in the future as well as scaling up things.
I'm happy that you brought this up because actually we do have a project that looks at application in urban areas to provide shading for the public. And that's in the context of a humanitarian project that our team member Peter Dine is directing in Freetown in collaboration with the heat officer Eugenia at Freetown. So they're testing different materials, including our MEER sheeting to cover a market, a public market. So effectively, that's one of the major applications. And one question we often get is, what about white roof? What's the difference between white roof and the MEER? I think the difference is very major, actually, for several reasons, both from a local cooling efficiency and also from a global cooling efficiency perspective. So locally, if you imagine you painted all the pavements, you know, white, what you would see is like a very bright, snowy day, except the sun is 5 times stronger than during winter, so you'll be completely blinding. And recent studies emerging out of thermal adaptation literature shows that if you increase the pavement albedo using these scattering and the diffusively reflecting white paint, you actually decrease the thermal comfort of the pedestrian and users. That's because you essentially send more light in opposite directions to everybody. Nobody can hide it from because the light is coming from every direction around you. So in contrast, if we had, say, mirrored pavement, then for certain orientations with respect to the buildings then and also solar angle, then there are locations where there's no light reflected because light reflects specularly in a controlled and predictable direction. So there will be so-called safe zones for pedestrians to pass through where there can be no stray light pollution. So that's a local cooling benefit and also scalability issue, because then we are not restricted only to rooftops where it's not visible from the ground, but also in locations on the ground, but since there's no light coming from the opposite direction, you don't care. And from global cooling perspective, most of the intense sunlight comes during the noon hours where solar angle is rather high. So if you can have a specular reflector to send it straight back up rather than randomly in every direction, it's the shortest path exiting the atmosphere. So the atmospheric exit efficiency also increases. So the fractional, the efficiency for global cooling also increases with the specular reflector relative to just white paint.
Yeah. So when you're talking about putting them on the roofs, I'm assuming it's mostly flat roofs as opposed to angled roofs. Is that what you're talking about?
Certainly the flat roofs would be perfect. There's no simulation or planning needed because it could only go up when the sun is above horizon, right? So, but in the case of a slanted roof, it really has to be judged on a case and by case basis. And ideally, eventually, new buildings would have to take into account in their design as to how to angle their roofs. So if, say, the roof is slightly tilting to the south for a building that's found in the northern hemisphere, then because the sun angle is, due south, then you would have most of the light sent upwards, either slightly straight up or maybe slightly, just at some angle that's, not going downwards. It's for roofs that are sloping towards slightly to the north in the northern hemisphere, which might be slightly problematic. But again, it doesn't really make sense to cover those roofs with mirrors because the projected surface area from the perspective of the sun is pretty small. It's like looking at my hand, it's big. If you're at a steep angle, there's barely any surface area, so it's useless to put mirrors there. Anyway, so it's less of a concern.
Thank you, Dr. Tao, for this fascinating discussion. And please, if you could, in conclusion, if you could just remind people how they can find you and how they can help your work.
All right, thanks, Paul. So thanks for the interview and also for the work that you do, to popularize climate science and bring it to the public, so we stay connected. I myself, was a physicist instrumentation builder, not really informed about the climate. So it's like people like Paul and also Professor Guy McPherson who are the first one to bring that message to even practicing scientists, engineers like myself. So there's a great value in the work that you guys do. So please support Paul and also Guy in their work. So if you want to support the MEER, so we are basically volunteer-run organization. I myself am not paid. I'm a volunteer full-time. All my directors are also volunteers, and they refuse to even take a temporary compensation when one of them had issues with their apartment situation. So we're fully committed, but we do need money to do the experiments that because otherwise it just won't get done. Like the large-scale experiments in Romania and also agricultural trials in Serbia and in Africa. We are attracting quite a bit of attention here, especially from people in the global south who are suffering, who understands the impact of global warming and drought and the deadly impact of such things. But unfortunately, in the global north, where I suppose most of the viewers are, the governments are not really, considering these things. They are not interested in saving yours, your lives and your future, your children's life, or those of people in the global south. So it's up to the public, the people of the global north, to really take matters into our own hands, to come up with the technology, share them open source, and spread them far and wide, and bring them to people who are suffering. So thank you very much in advance for anything that you can do for the project.
Thank you, everybody, for taking the time to listen to these fascinating ideas, and it's much more than ideas. There's experiments, and things are being scaled up, as we speak, for the MEER technology with Dr. Yitao. And so, thank you for listening in on this Climate Emergency Forum video, and please remember to subscribe and click on the links to subscribe to the channel.